Good evening. Welcome to your fresh approach to our series in Harmony with Nature. I'm your host, Shalom Mandeville, and in the center is a biologist, Peter Shacklock, who is a co-host. I'm extremely proud to present to you Dr. Eville Gorham on my far right. Dr. Gorham was born in Halifax, and he obtained his doctorate in London, and he practiced research and was a professor in London and Toronto, and now he's the professor of ecology and behavioral biology at University of Minnesota in Minneapolis. I would be failing in my duty if I didn't mention that Dr. Eville Gorham was the one who first fingered acid rain back in the, I think, late 50s. And he also found a connection between acid rain and human health. So I'm extremely proud to have Dr. Gorham as our host. Dr. Gorham, in the last show we spoke about peatlands and bogs and marshes in a more or less a very rural perspective. Now, what do you feel about preserving bogs and wetlands around lakes and rivers in an urban perspective, like within a city?
Well, my view is that they're the last bits of real nature we have in the city. They offer school children, for example, a chance to take field trips from their schools out to the wetlands to see nature operating in the way she has done for time immemorial. You don't see that if you go to a rather well-manicured park or a plantation of trees. The wetlands really do show us how nature works, and as I say, they're often the last bits where we have real nature, where we can see the birds that normally inhabit that area, where we can see the insects, the frogs, the snakes. They're a marvelous resource for young children and for the school teachers who have to teach those young children as well. Also, I think they bring an aesthetic value to urban life. The very fact that they're there and you can go and take a look at them, see the ducks nesting or the birds in the trees, listen to the peepers peeping in the spring, that does something for a lot of people. You know, we live an urban life, but I sometimes wonder if we aren't programmed genetically to have a feeling for nature. And the reason I say that is that most of us like to grow things. We like to keep pets. In its most debased form, you can see it in the wish to have plastic flowers around or pink flamingos on your lawn. That says something about our human nature. So these wetlands are often the last bit of nature that's accessible to urban livers, and I think it's important that we keep them.
And the biologist Peters also tells me that they will protect the lakes and rivers from pollution. Would that be a reasonable assumption?
They can do. Many peatlands, wetlands that deposit peat, store a lot of nitrogen and phosphorus in those peat deposits. They may also send a lot of nitrogen back to the atmosphere in one way or another by the action of the microbes in the peat. So yes, they can have an effect on nutrient inputs to lakes. They can indeed protect them to some degree. It depends on the rate of flow and the amount of wetland. But they are important in that respect. They can also serve as basins to catch silt and so on, so that doesn't discolor our streams and rivers, although it will indeed add nutrients to the wetland, and if it's an acid peatland, those inputs of silt will change it. We're seeing a lot of our sphagnum bogs with tamarack on them being converted to cattail swamps, where roads have been built through them, where the road fill allows calcium lime to leach out of the material that's used as roadbed, and that alters the nutrient status. So what was a nice tamarack swamp with leatherleaf and Labrador tea and sphagnum moss will turn into a cattail marsh with blackbirds. So they're nice too, but we have to think carefully about how we treat our wetlands. We can easily alter them. They're very fragile. They're very subject to disturbance if we alter the hydrology, the water table, or the rate of water flow. They're also very sensitive if we change the nutrient conditions by adding lime or nitrogen and phosphorus in wastewater.
I guess we should move on to the topic for today, which is acid rain. And I understand that you and Dr. Underwood from Halifax are doing some studies of lakes and looking at the causes for acidification.
Yes, that's right. John Underwood's an old friend of mine. He studied with me in Minnesota for a while before he came back to Nova Scotia to work for the Department of Environment. And we got together to look at the vexing question of whether there is natural acidification of lakes. Now, there's been a long and very controversial debate about whether acid rain was acidifying lakes or whether it could be natural processes such as forest growth, where forests are regrowing, whether they would tie up the lime and so on from the soil so that the decay of the forest humus would produce acids which would acidify the lakes. And so we decided we would try to set out and solve that problem, find out whether in fact there are natural causes of lake acidity, whether indeed acid rain is another cause, and whether the two are additive. So what we did was to take a look at some Nova Scotian lakes, and I have some slides to show just what we were up to there. We start, of course, with the sort of classic picture of a lake in a pristine state. This is one of the lakes in Halifax County where we first did most of our work. And what I have here is a rather old slide. There are more up-to-date ones, but here the black areas show areas that are sensitive to acid rain because of the nature of the geology. The black areas are granites or quartzites, in some cases Halifax slate, that doesn't have a lot of basic material and a lot of lime in it to neutralize the acid deposition as it falls. And you can see that much of Nova Scotia is sensitive. Now, I'll stress that that is an old slide and there are more up-to-date pictures, but in general, Nova Scotia is a sensitive area for acid deposition. Here you see the acidity of the rain marked by those lines, ISO lines going through the province. Down in the southwest, that curving line is probably a pH of around 4.5. I can't see it very clearly. And it goes up to the high 4s and perhaps the low 5s in Cape Breton. The pH, the lower the pH, the more acid the rain, and the more likely we are to have lake and stream damage. So the southwestern part of the province is receiving the more acid rain generally. The northern part in Cape Breton is receiving the least acid rain. Now, I should make an exception around Halifax itself, where there is a big urban area that is generating a lot of sulfur dioxide, which is the major cause of acid rain. And the whole urban area generates, as I say, lots of sulfur oxides. The point we took as our reference, though not the sole contributor, is the Tufts Cove power plant. It's a contributor, although it has reduced its contributions of sulfur dioxide very remarkably in the last several years. So we used that as a sort of center point about which to locate lakes for study in Halifax County. And we chose a whole variety of lakes. Here's my colleague John Underwood taking a sample in December from a lake near Halifax that's surrounded by conifers. Now, in that lake with coniferous trees around it, you get a soil profile developed like this. Just under the notice SL201 is a very organic layer of decomposing humus from the falling needles, and that generates colored organic acids. But they also leach down into the mineral soil, and they take the iron and aluminum out of the immediately underlying soil, which is left bleached white, as you see in that white layer there. Those organic acids and the associated metals, aluminum and iron, leach into the deeper soil, and down there, where it's less acid than in the surface organic layer, those organic acids with their metals are precipitated, so that very little of the colored organic acids escape where you have mineral soil with a profile like this. So these coniferous forest lands don't seem to be major generators of colored organic acids. Rocky barrens don't have those deeper mineral soils, and we suspect that they may be generating a lot of colored organic acid to go into our lakes. And our recent studies on streams in southwestern Nova Scotia suggest that this is true, although we're just in the process of working up the data. So rocky barrens may be important. But the major source of natural lake acidification is peat bogs. And this is Pebblelogich Lake down in Kejimkujik. And along the southern boundary you see a big peatland with a stream draining through it. And that stream will be dumping in heavily brown-colored water. It'll look like tea. So that Pebblelogich Lake is a tea-colored brown water lake, and it's probably acidified mainly by organic acids, at least for most of the year, except during perhaps spring melt or when you have a heavy flush of acid rain. So it's these peat bogs that we got interested in. Were they the major source of natural lake acidification? And so we studied a lot of lakes with peat bogs around them. There's John Underwood in the red hat. Pete Ogden is out there, Joe Carricus, biologists who are well known in this area. And on the far side, you see that brown area of bog surrounding the lake, and that, too, is a tea-colored lake. Now, if you look at Nova Scotian lakes and their pH, remember, the lower the pH, the more acid the lake, you see that they tend to show a bimodal frequency. The number of lakes is what's shown by the vertical axis, the acidity along the horizontal axis, and you see two modes. You see that the lakes either tend to be up at high pH around above 6.5, close to 7, or they tend to be down around 4.9, with very few in the middle. That suggests that there are two things controlling lake acidity. One is the base supply from the soil, and as long as that's adequate, the lakes will be up around pH high 6 to 7. If the acid loading is heavy enough, either from acid rain or from bog acids, suddenly the capacity of the bases in the soil to neutralize the acid will be overcome, and the lake will shift to a low pH. So you tend to have two modes of pH here, circumneutral or acid. And the question is, what is causing those acid lakes? Well, what we did was to look at the contribution of hydrogen ions, which are the cause of acidity, and that's on the right-hand vertical axis. The data are shown as pH on the right-hand side, hydrogen ion on the left-hand side. And what we did was look at what we could relate the hydrogen ions to, what we could relate those acid hydrogen ions to. And we found that that the higher the dissolved organic carbon, which is the backbone of those colored organic acids, the higher the hydrogen ion concentration. So the curve marked DOC, dissolved organic carbon, shows a clear relationship. The higher the DOC along the top horizontal axis, the higher the hydrogen ions. But we also found that non-marine sulfate, that is sulfate in the lake waters corrected for sea salt sulfate coming in from sea spray, also showed a strong correlation with the hydrogen ion. And so the fact that hydrogen ion correlates both with dissolved organic carbon, the proxy for the colored organic acids, and with non-marine sulfate, the proxy for sulfur dioxide from industrial urban sources, says that the acidity of the lakes in Halifax County is due to two causes. It's due to bog acids, a natural process. It's due to acid rain. And the two are additive. Now, the declining curve, especially the one for calcium, shows that as you increase calcium along the bottom horizontal axis, as calcium gets higher, then hydrogen ion drops. And that shows the capacity of the soil to neutralize the acidity. So the balance of the acidity is owing to the interaction of soil factors, the amount of base that's present in the soil, the amount of acid loading from natural sources such as peat bogs, and the amount of acid loading from acid rain. And these are additive. Now, we can see here, remember, we were using the Tufts Cove power plant as a center point for our distribution of lakes. It's not the major source within the urban area, but it's part of the urban source. And you notice that if you look at lake water sulfate along the vertical axis, which has been corrected for sea salt, that's the acid rain component, the acid rain source, is ultimately SO2 from power plants and urban industrial activities. That the acid, the non-marine sulfate rises as the distance from the power plant and from the urban source declines. So the closer you get to the city of Halifax and its power plant, the higher the acid rain component from sulfur dioxide. And so that shows that we have a local source of urban pollution that's causing lake acidification here. But the arrow shows a baseline for where the long-distance sulfate lies at about 40 microequivalents per liter. And that is the long-distance acid rain component coming mainly from the eastern United States and central Canada. So there's a sort of baseline input of acid rain materials coming from long distance, to which we're adding the local urban source here in Halifax to acidify Halifax County lakes.
It looks like the local additions are about 2 to 3 times.
They can't, at at the point of origin, or very close in. They're very significant, close into the source, but they decline rather rapidly away. And it's that huge urban industrial center, east central part of the continent, that is providing the general baseline for this urban addition. Now, one of the things we looked at was where is all that colored organic acid coming from? And although the dots are rather scattered, the relationship is statistically highly significant. What that shows is that dissolved organic carbon, or DOC, the carbon backbone of these colored organic acids, rises as the ratio of muskeg or peatland to lake area increases. So it looks as though we have a bog source. Now the scatter there is rather great, partly we thought because we weren't able from the maps provided by Nova Scotia Lands and Forests to interpret what was upland conifer forest and what was conifer swamp. So the conifer swamps we could not include in our ratio, and that has led us to do some further work in southwestern Nova Scotia on streams where we're trying to sort out the individual peatland components and their influence. But that does show clearly that the more peatland in the area, the higher the colored organic acid content of the water will be. And the significance of that may be for the fish populations. This is a salmon. It looks a little different from the normal salmon because it's very much younger. And when I started at Dalhousie, this was the sort of organism I spent my time researching. But salmon, young and old, can be hit hard by acid rain, and it's perhaps more than a coincidence that the salmon rivers that have lost their populations tend to be in the peatier parts of the province. Now, it may well be, although it's not nailed down tight, that the natural acidification of our lakes by peatland drainage has brought the lakes and rivers close to the danger point, and that acid rain has added enough to tip the balance in those rivers so that their fish populations have dropped out. As I say, that's informed hypothesis. We don't have it nailed down, but the evidence, I think, certainly warrants a lot more work, and several people feel that that's probably the most reasonable explanation for why the salmon rivers have shown this startling decline, that we've probably added acid rain to stress lakes already close to the danger point because they've received acidification naturally.
Is that what they call as the alevins?
No, this is at the fry stage, before the alevin stage. It's still got the yolk sac there that it relies on until it can feed for itself. Incidentally, that yolk sac can be damaging because, as you know, chlorinated hydrocarbon pesticides tend to concentrate in fatty tissues. So little beasts like this have a lot of these materials stored in the fats in their bodies, and as they use up their fat reserves, those pesticides are mobilized, and so the time at which the yolk sac is absorbed is a time of great sensitivity to pesticide toxification.
I have one question, more of a technical question about the measuring the pH. The first time you measured the pH, did you think there might have been something wrong, like you got some contamination, since there's very little buffering capacity?
Well, it's certainly these are relatively poorly buffered waters, but by and large the current generation of glass electrodes are pretty good. When I first started measuring pH in Halifax County back in the 50s, I didn't really know what to expect. So I went out and I took a look and took a lot of samples and analyzed them. And when I saw that some were acid, I noticed that the more acid ones were often highly colored. And I thought to myself, well, this is just natural. Everybody knows that bogs are acid, so the peat bog drainage is acidifying Halifax County lakes. About 10 or 12 years later, Walton Watt, who's with the Department of Fisheries and Oceans down here, repeated that survey to see if the lakes had gotten any more acid in the interval. He found they had gotten somewhat more acid, but he found something I hadn't looked for or seen, that the closer you got to the center of Halifax with its urban air pollution syndrome, the more acid the lakes became. So he suggested that the lakes were acid chiefly because of air pollution. And when I read this, I scratched my head and thought, well, I hadn't thought of that. But why is the relationship there to color and to dissolved organic carbon? And that was one of the reasons that led me to come back and work with John Underwood on this problem, that I was not convinced that I was wrong. As it turned out, we were both right. Walton was right that air pollution was involved. I was right that these bog acids are involved. And unfortunately, that's bad for the fishery if you have two sources of acid adding one to another.
Well, a lake being acidic, more things are going to dissolve. Is that not true?
Well, certainly the more acid the lake, the more aluminum you will dissolve, and aluminum is another major problem for the fishes. As you add acid, you get more and more aluminum dissolved from the rocks and soils and from the sediments in the lake, and this clots the fish's gills and interferes with its salt metabolism. So this can be a real killer, and this is often a cause of rather sudden fish kills in lakes. As you pour in acid that percolates through the soil, releases a lot of aluminum, this really gives the fish serious problems. So you can both have a direct effect of the hydrogen ions, the acids themselves, or you can have a secondary effect owing to mobilizing aluminum and interfering with the fish's gills and with salt exchange. And this can be very serious indeed.
That would be the same for other minerals too, because I think almost every mineral dissolves better in an acid than it will be in.
That's right, but the problem is that the more acid the soils become, the more they've lost of all the bases. The more they've lost, the less easy it is to weather. So although there's more weathering potential in these acid lakes, the substrates, the soils and rocks have often been so depleted that even the more acid conditions can't bring enough calcium out of the system to make it a good fish habitat. I might also add that the more organic acid you dump in from these colored organic acids, the less toxic the aluminum becomes, because the organic acids complex with the aluminum and make it much less toxic. So these bog lakes probably have not had the aluminum problem that the Clearwater lakes have had when they've been stressed by acid rain. There, aluminum has become a very important secondary toxicant.
How about flushing? How do you figure that?
Well, flushing rate is important, of course, and the more rapidly a lake flushes, the more subject it is to spring melt acidification. In this part of the world, you don't have a buildup of a snowpack over the whole year as you do in perhaps the Adirondacks or in northern Michigan. There, the snowpack builds up all through the year. All the acids are concentrated in the intercrystalline brines in the snowpack, and the very first melt brings out all these impurities that have been frozen out into intercrystalline brines. They leach out with the first meltwater and give a sudden flush of acidity that is very toxic, that's devastating to fishes. In Nova Scotia, you don't have quite such a buildup of snowmelt, but you can have sudden flushes of heavy storms bringing in a lot of acid if they come from the right wind direction. And if those occur and flush out a lake with a short residence time, then you can have those kinds of problems again.
How about the opposite? Flushing out with fresher water, not fresher water, but less acidic? So
well, of course, it may disappear more rapidly too. If you have storms bringing in acid, and it's not quite toxic enough to kill the fish, it may be gotten rid of before the next acid flush by a flush of water that is circumneutral or much less acid if the wind blows from a different direction. So, yeah, flushing time can be very important to the responses of the lakes.
I was thinking, Dr. Gorham, you were just telling Peter here, about the problems of the peat and bogs and marshes. But then, on the other hand, I was always brought up to believe that you need these things in a buffer. So, where is the happy medium? Because I'm involved in actually three advisory boards, and I've been pushing like anything to preserve wetlands.
Well, I'm biased. I'm a wetland ecologist, and I like these habitats, and I think they deserve very careful consideration. Certainly, there are lots of them. If you have 14% of Canada covered by wetlands, you can afford to spare some for development, certainly. The critical thing is that you look at the wetlands before they're developed, see whether they are common types that you can easily afford to lose, look to see if there are endangered organisms in them, look to see whether they have a unique contribution to the local area as a nature reserve for school children and so on. If you can meet all these criteria and say, well, we have plenty of wetlands, these are not rare types of wetlands, the organisms in them are fairly representative of the general run of wetlands in the place, and we don't have a need for wetlands in this area, then maybe you can say, well, certainly develop them. But what I'm calling for generally as a wetland ecologist is that we take a very serious look before we destroy a wetland. Very difficult to reconstitute them, almost impossible to reconstitute them in their original state. So before we simply dismiss them as wastelands to be reclaimed, as the popular jargon goes. Let's take a look at the values they have to the community, their value as buffers along the margins of lakes, their values as nature reserves, their value in contributing a unique kind of ecosystem to the world that we'd be poor without. And only after you've taken a look at all those things and satisfied the citizens that it's a reasonable thing to develop here, do you go ahead. All that most of us are calling for is careful consideration and due protection of the rarer, less representative elements. Where we have lots of wetlands, we can certainly afford to spare some. And none of us are calling for a total halt to wetland development. What we're calling for is a careful consideration. If the wetland destruction gets very severe, as it has in parts of the United States, and certainly in the prairies of western Minnesota, then we have to demand that for every wetland that is destroyed, not only do we make sure that it's one we can afford to lose in the sense that it's a common type, we may demand that it be replaced by a constructed wetland. And wetland construction is becoming quite a feature of many states that have destroyed much of their wetland. And so in areas that are not rich in wetlands or that have destroyed most of what they had, then it may be necessary to say no net loss. For every wetland you destroy, you must construct one, and you must not destroy those that are representative of unique habitats or unique organisms that we can ill afford to lose. Now, the yellow-eyed grass is an interesting case in point. Here in Nova Scotia and along the coastal plain, there's lots of yellow-eyed grass, and we could afford to lose many stands of it before it would become an endangered species. In Minnesota, we have 6 stands that we know of in the state. If we lose those, we've lost them all. Now you may say, well, why not just import some from the coastal plain? We've got lots of it in Nova Scotia. Let's get Nova Scotia to send us out some stands, and we'll plant them and restore them. A, we don't know enough about the ecology of the yellow-eyed grass to know that we can make it take in those other wetlands where it doesn't currently occur. B, there may be unique genetic strains of the yellow-eyed grass that are adapted to the very margins of its range out on the prairie that are not the same as the genotypes that are here in Nova Scotia. And again, we can't afford to lose them. Now that relates back to the salmon problem. Each salmon strain that homes on a given river is genetically distinct and has been adapted to that river system through millennia of evolution. So that if we destroy that genotype in that river, we can't say that the river down the way, 10 miles down, 100 miles down the coast, will provide us with the same strain of river to recolonize. We may have lost something genetically unique. We haven't lost the species, but we've lost some unique genotypes, and we want to think about that. They may be genotypes we will need in the future. We don't know.